Hello. Today, we're going to dive into the fascinating world of periodic phenomena. These are situations where a pattern repeats over time, like the phases of the moon or the swinging of a pendulum. In this video, you will learn to construct graphs of these relationships from a description and describe their key features, such as the period. So, what makes a relationship periodic? A periodic relationship shows a repeating pattern of output values over successive, equal-length intervals of input values. Think of it this way. As the input, like time, increases, the output, like a height or a temperature, goes through the same sequence of changes over and over again. The cycle of seasons, for instance, repeats every year. This idea of repeating behavior is the fundamental concept behind periodicity. A key concept when discussing periodic relationships is the period of the function. The period, which we often denote with the letter k, is the smallest positive value such that the output of the function at x plus k is the same as the output at x. This holds true for all x in the function's domain. Let's rephrase that. The period is simply the horizontal length of one complete cycle of the pattern. It's the minimum amount you have to shift the graph to the right to get the exact same graph back again. Knowing the period is powerful because it tells you that the function's behavior is entirely determined by any interval of that length. For example, if you know what a periodic function does over a period from x equals 0 to x equals k, you know what it does everywhere. You can use this cycle to predict what the function will do at any other time, or to recreate the entire graph by repeating the pattern. Now, let's learn how to construct a graph of a periodic relationship when you're given a verbal description. This is our first learning objective. Our objective is to be able to create a graph from a word problem. To do this, we need two key pieces of information from the description. First, we need the initial conditions. This tells us where the cycle starts. Second, and most importantly, we need to understand the behavior of the function over a single cycle. This is the pattern that will repeat. Let's work through an example to see how this is done. We'll start with a classic periodic system, a spring. Imagine a spring attached to a wall with a weight at the end. We're going to graph the weight's height above the floor over time. This is a very common physical model. First, let's find our starting point and the height at rest. The problem states the weight hangs at 5 feet at rest. So we'll start by labeling the x-axis for time in seconds and the y-axis for height in feet, and draw a horizontal line at y equals 5. This is our equilibrium or rest position. We've established the rest height of our spring as 5 feet. Now let's follow the description to find the starting height and the cycle's amplitude. The problem says the weight is pulled down 3 feet from its rest position and released at time t equals 0. If it starts at 5 feet and is pulled down 3 feet, where is it released from? The starting height, at time 0, is 5 feet minus 3 feet, which is 2 feet. So, our first point on the graph is 0, 2. Let's plot that on our graph. The amount it's pulled down, or pushed up from equilibrium, is called the amplitude. Here, the amplitude is 3 feet. The problem also gives us a second piece of information to help define the cycle. It tells us the weight takes 2 seconds to complete one full cycle and return to its lowest point. This is the period of our function. The graph should take 2 seconds to repeat its behavior. We now have 2 low points, the start at 0, 2, and the end of the first cycle at 2, 2. This means the cycle must reach its highest point halfway in between them, at t equals 1 second. Since the amplitude is 3, the highest point is 5 feet plus 3 feet, which is 8 feet. So we can plot the point, 1, 8, and sketch the first complete cycle of the spring's oscillation. So, just from a verbal description, we've successfully constructed the graph of one cycle of this periodic relationship. Now that we have one cycle of the graph, our learning objective is to describe its key characteristics. Let's look at the graph we just created. The first and most important characteristic is the period, which is the horizontal length of one full cycle. We can see our graph starts at a minimum, goes up to a maximum, and comes back down to a minimum. How long does that take? One full cycle on our graph takes exactly 2 seconds. The period of this function is 2 seconds. We can estimate this period by observing where the pattern starts repeating. What other characteristics can we identify? We can see that the graph has a minimum value at 2 feet and a maximum value at 8 feet. The midline, or equilibrium position, is right in the middle at 5 feet. This matches the verbal description. We can also see intervals where the function is increasing and decreasing. From t equals 0 to t equals 1, the height is increasing. From t equals 1 to t equals 2, the height is decreasing. We can also talk about the rate of change. Notice the curve is steepest near t equals 0 and t equals 2, where the weight is moving fastest, and flat at t equals 1, where the weight momentarily stops at the top of its bounce. Let's work through another example to solidify these concepts. This time, we'll consider the temperature in a house over a day. Here's the scenario. The thermostat is set to cool the house when the temperature reaches 75 degrees, and to stop when it hits 70 degrees. Over a day, the temperature goes from 70 to 75 and back every 2 hours, starting at 70 degrees at midnight. Let's follow the steps. First, graph the initial conditions and equilibrium. The problem states the temperature is 70 degrees at midnight. So we plot the point 0, 70. The temperature will cycle between 70 and 75 degrees. Next, let's identify the period and maximum. The problem says the cycle is 2 hours long, and it goes from 70 to 75 degrees. The period is 2 hours, and the highest temperature is 75 degrees. Since the cycle is 2 hours long, the pattern from hour 0 to hour 2 will repeat for the entire 8 hours we need to graph. If it's at 70 degrees at time 0, and it goes up to 75 degrees over 2 hours, it must reach the maximum of 75 degrees at the midpoint of that interval, at t equals 1 hour. It then drops back down to 70 degrees by t equals 2 hours. This is our first complete cycle. To graph for 8 hours, we just repeat this 2-hour cycle 3 more times. The cycle from t equals sine 2 to t equals sine 4 will be identical to the first. It will be 70 at t equals sine 2, 75 at t equals sine 3, and back to 70 at t equals sine 4. We do this again for the interval from t equals sine 4 to t equals sine 6, and a final time for t equals sine 6 to t equals sine 8. By simply repeating the pattern of a single cycle, we can generate the entire graph for the specified duration. This is one of the most powerful and efficient ways to represent periodic functions. Now let's apply our second learning objective to the house temperature graph we just created. We want to describe the characteristics of this function just by looking at its graph. First, the period. The temperature cycle repeats every 2 hours, so the period is 2 hours. Next, the minimum and maximum temperatures are 70 and 75 degrees respectively. The midline, or average temperature, is 72.5 degrees. Now for the intervals of increase and decrease. Notice how the pattern repeats. The temperature increases in the intervals from 0 to 1, 2 to 3, 4 to 5, and 6 to 7. The temperature decreases in the intervals from 1 to 2, 3 to 4, 5 to 6, and 7 to 8. This demonstrates a crucial principle of periodic functions. Any characteristic you find in one period, such as increasing or decreasing intervals, will be found in every period. The function is predictable. So, we've explored how to build graphs of periodic relationships from verbal descriptions. We've seen that to do this, we need to identify the initial state and the repeating pattern, or cycle. We learned that the key to understanding a periodic function is its period, which is the length of one complete cycle. Once you have that, you can construct the entire graph. We also learned how to describe the key characteristics of these functions. What are some of those key features? We looked at the period, the minimum and maximum values, the midline, and the intervals where the function increases and decreases, and we saw that these characteristics are consistent across the entire function. This ability to translate a real-world scenario into a graph and then describe that graph is a powerful skill. It allows us to analyze and predict the behavior of many systems, from engineering to biology. Remember, the world is full of repeating patterns, and with the tools we've covered today, you are now much better equipped to understand them.